Hello everyone, we are back again solving still substitution reaction problems. In this chapter or in this series we will be looking at solvents that are used most commonly in substitution reactions. So before we go deep into the mechanisms of SN1 and SN2, one of the important factors in substitution reaction is the nature of solvents. So the solvents that are common in nucleophilic substitution are polar solvents, obviously, but the polar solvents are also divided into protic and aprotic ones. So here in this question, you are required to classify this number of solvents as protic and aprotic ones. So when we say protic solvents, these are solvents that contain a hydrogen on an electronegative atom. For example, it could be NH, it could be oxygen H, it could be, for example, HF, like on fluorine, it could be on chlorine, etc. So this hydrogen is what makes that solvent aprotic. This hydrogen also makes that hydrogen protic. So these are the protic components of the solvent. So in the first question, that's a very good example of alcohols. In general, all alcohols contain a protic hydrogen. That's why they are called protic solvents, are alcohols. So in general, ROH, R refers to the alkyl group, that means the carbon component, but you have this hydrogen that's directly attached to the oxygen. So that's why this alcohol, in general, functional group, are protic solvents. Protic solvent. So this is an isopropyl alcohol. It's called isopropyl alcohol. It is a protic solvent. So from our lecture discussion, we have already said that protic solvents are good for SN1 type reaction. So isopropyl alcohol is a protic solvent which is good for SN1. Here you have nitromethane. So the structure of this nitromethane is like this, NO2. Obviously it is polar solvent, but the hydrogens are not on an electronegative atom, so they are not capable of making hydrogen bonding. So this is not a protic solvent. So this is aprotic. So in a substitution reaction, it could be used as a substitution reaction for an SN2 type reaction. So it's aprotic solvent. You have dichloromethane. Still, these hydrogens are not on chlorine, or they are on carbon. This therefore is not protic, so it's aprotic solvent. So the polarity is not also not that significant, so I don't think this would not practically be used in any substitution reaction. In any case, it's aprotic solvent. Here you have ammonia. This is NH3 with 3 hydrogens that are capable of doing hydrogen bonding, and the hydrogens are on nitrogen. So this is a protic solvent. Protic solvent. So it's potentially could be used in SN1 type reaction. So the next one is trimethylamine. even though it's an amine the same way, the same functional group, amine, but the hydrogens are all substituted by carbon, and the hydrogens are not on any electronegative atom, they are actually on carbon. So this is aprotic solvent, and it's kind of polar, so we can use it probably in as a SN2 mechanism. Here the last one, you have formamide. You have the structure is like this. So practice also how the structures look like to draw. So these are hydrogens, the two hydrogens. So these are the two hydrogens, and this is the one hydrogen. So this formamide is on, this is not the one which made it this compound to be protic. Rather, these two hydrogens are the ones which are on nitrogen that makes this solvent as protic solvent. So that could be an SN1 mechanism can be done in this solvent. So here as a summary, I'm just showing you one, it's very easy to identify protic and aprotic solvent. Protic ones are easy to pick because you need just to find hydrogen that's on an electronegative atom. And once you identify what kind of solvent that is, you can also identify what mechanism can be used. All protic solvents are good for SN1 mechanism, and all SN2 reactions are run in a polar aprotic solvent. So in summary, this is what we have on protic and aprotic solvent. So I'll continue to the next. Okay, let's continue. Here I have a very simple looking question, and you can answer very easily, but it's an important concept to discuss. So you have an amide and an amine in the same compound, and the question is why the amide nitrogen, the amide nitrogen is this amide nitrogen, is less nucleophilic than the nitrogen on the amine. So there are two nitrogens that contain lone pair of electrons, but one is more nucleophilic than the other. So the question is why? So let me redraw the structure so that it could be very evident. The amide is this one, and CH2 and CH3H. So the question is asking why the amide nitrogen, which is this nitrogen, the amide one is this one, is less nucleophilic, meaning that obviously always nitrogen has lone pair of electron when it's bonded into three species, three groups. This is also lone pair of electrons. So why is this is less nucleophilic than this? That means if you were to run a nucleophilic substitution, the electron, the nitrogen that goes and attacks the leaving group or the carbon is this one, is more nucleophilic, but not this one. So this is less nucleophilic. So this can be easily answered by a simple concept you have learned at the beginning of the course, that is resonance. Resonance can explain that. But before I go to resonance, why is this more nucleophilic? Meaning that it's showing you that this pair of electrons are more available to attack an electrophile like alkyl halide. If you have an Rx, this is a nucleophile, electrophile, this lone pair of electrons can attack this, and this can live as a leaving group in a substitution reaction. But this lone pair of electrons, there are two of them, the same lone pair of electrons, they look like, but they cannot do this. They cannot do that. Why is those lone pair of electrons are less nucleophilic? Reason is they are not available as this ones. They are not available because in this structure, I'll just put it like again, rewrite it. This lone pair of electrons have a potential to resonance stabilize themselves by being pushed to this bond, and this one now becomes out. Because resonance always stabilizes, and it makes opportunity for the electrons to be move within the molecule, it cannot do the attack, and it's less available because it's resonance stabilized. So the resonance structure for that would be, of doing that, gives you double bond nitrogen, okay, H, CH2, NH, CH3. So because of this resonance stabilization, because of this resonance, these electrons are not available. They are stabilized within themselves. Resonance has a possibility to stabilize any structure. That means the electrons are not available to go somewhere else out, because they have also a chance to delocalize within the molecule. So resonance explains why this is less nucleophilic than the other one. The other one, it cannot push any electron. Remember, I have a piece on resonance within my lecture series. Resonance is where you have a pi bond system where you can push the electron into a pi system. So because it is next to a pi bond, you can push this. This is sp2 also carbon. You need to have an sp2 or an sp hybridized carbon. You have sp3 here. You have sp3 hybridized carbons. They are not allowing you to do any resonance of those electrons. Sigma bonds cannot do resonance. So that those electron pairs, lone pairs, are available to go and attack. So this is a more basic. Between this nitrogen and this nitrogen, this is the most basic nitrogen, because those lone pair of electrons are available. So this nitrogen is more basic, more nucleophilic. This nitrogen is less basic, not available. They are not available to be used as a base or as a nucleophile. So resonance is an important concept in this regard. So this nitrogen of the amide functional group, is less nucleophilic than the amine. So let me generalize here. R NH2 versus R NH2. This lone pair of electrons are more strongly basic, strong base, and more stronger nucleophile. Here, because they do this resonance, they are less available, less basic, not a nucleophile. Okay, these are the distinctions. It's an important concept in your studies, so make sure that you understand this Looks simple concept, but it has a lot of explanation under this. So amide nitrogen is less nucleophilic, less basic than amine functional group. So this is amide functional group. This is an amine. So if you are asked, an amine is more basic than an amide. The amide one lone pair of electrons are resonance stabilized. Hence, they are not available to be basic or to be nucleophilic. So very important concept. So we'll continue to the next. Okay, here we have a very important question that almost summarizes the chapter on nucleophilic substitution. So we'll go each one step by step. So here you have a primary alkyl halide. This is primary alkyl halide, a bromo compound, a primary with 5 carbon, 1, 2, so it's bromopentane, 1 bromopentane, a primary carbon, and you have a cyanide nucleophile. It could have come from potassium cyanide, sodium cyanide, so it could be also given like this, so you should be confused. The potassium doesn't do anything, so in a reaction we are just given the nucleophile. But this cannot just come by itself in a bottle, so it's potassium cyanide or sodium cyanide. In any case, that's the nucleophile. And solvent is acetone, so that is polar aprotic solvent. Everything what you see here immediately tells you what is the mechanism. So in any case, first let me give the product without showing the mechanism. So the product would be 1, 2, 3, 4, 5 carbon CN, substitution by a cyano group. That's the nucleophilic substitution product. That's product. Now it asks us in A, show a mechanism. So just by looking again back what is given in the reagent, you have a primary alkyl halide, you have a nucleophile, strong nucleophile, you have a polar aprotic solvent. Immediately, what's the mechanism of this reaction? This is SN2. So one question is, big question is answered. The reaction is an SN2 reaction, a primary alkyl halide, a polar aprotic solvent, and a good nucleophile. Show a mechanism. When you are asked to show a mechanism, you are going to show the arrow with the proper direction of attack. So now the mechanism for this reaction would be, if we have to draw it again, 1, 2, 3, 4, 5, bromine. Always we have said that it's a backside attack. You have a cyanide with a pair of electrons. It comes and attacks that carbon. That's the electrophilic carbon. We call that electrophilic. This is nucleophilic. That is electrophilic. That means the positive center. In SN2 reaction, bond breaking and bond making happens simultaneously. So there is no multi-step. While this is attacking, the bromine leaves to give you that product. So if the SN2 mechanism is like this. Backside attack of that carbon, bromine leaves. So show mechanism is what it means to show with arrows, proper arrow in direction. Second question is to draw energy diagram. Assume that this reaction is exothermic. That's what it means here. So it's asking you draw energy diagram. The energy diagram for an SN2 mechanism doesn't involve intermediate. It is a single step mechanism. So hence I will write the energy diagram here. Sorry for the space, but You have X and Y axis like this. This is energy, and you starting material here. You reach to the transition state, no intermediate, and product is formed. SN2, single step. It is a single step reaction. So a cyano and the RBR, meaning the alkyl halide, are the starting material. Now in the transition, this is the activation. So you have to label everything, it says. So this is the activation energy, EA. You have to label properly. And the delta H of this reaction, because you are told it's exothermic, so the energy of the products are lower than the starting materials. So delta H is this much. Heat of the reaction is delta H. Here it's the progress of the reaction, This is the transition state. The highest energy is the transition state. So it asks us, that's enough for the energy diagram. Here it asks you in C, draw the structure of the transition state. Draw the structure of the transition state. In SN2 reaction, the bond making and the bond breaking happens simultaneously. So in the transition state, both are implicated, both the nucleophile and the leaving group. So what it looks like would be cyano start to form a bond to this carbon right here, okay, and a bromine start to leave. So this is, there are two hydrogens in here, right, and the rest is this. 1, 2, 3, 4, 5 carbon. So at the tip, that's what happens. Cyano is start to attack, meaning to make a bond. The Br is loosening up. So this is the transition state. So it's, both of them are implicated. So that's the transition state for an SH2 mechanism. Now, this is transition state. It is right here. So the transition state complex is here. That's high energy. High energy. Transition state structure is very high energy. It is 5 coordinated because 1, 2, 3, and 2 hydrogens are there. So it's a penta-coordinated carbon, basically. This is how it looks like, penta-coordinated carbon, high energy. What is the rate equation for SN2? SN2, both the alkyl halide and also the nucleophile are implicated in the transition state. Hence, the rate equation is, R equals rate constant times the concentration of the cyano is important, and the concentration of the alkyl halide, 1, 2, 3, 4, 5. Both, this is the rate law. So the rate equals rate constant times the concentration of cyano, nucleophile, and alkyl halide. Now it's asking you about this in E. All of the questions are related to what would the rate be when things happen. For example, if the leaving group is changed from bromine to iodine, what would be the rate? It's not in quantitative way, but analytically or qualitatively, what do you say? Instead of Br, if you had I minus for the same condition, would the rate be faster or slower of the substitution? basically the question is asking you if the leaving group was iodide versus bromide, which one is, what would happen to the rate. So if you just see bromine versus HI, that's how you'll see it. If you see the conjugate acids of HBr and HI, HI is a very strong acid, okay, and the HBr is a weaker acid than that. So Br would be a strong base, a stronger nucleophile, but I minus would not be a stronger base. It would be a weaker base. That means it's a good leaving group. As a nucleophile, that would be weaker. Therefore, it would be easier for it to leave. So I minus is a better leaving group. Therefore, if you change from bromine to iodine, rate would be increased. I don't know how much, but rate would be increased. A leaving group, because I minus is better leaving group than Br minus. Br minus better leaving than chlorine. Chlorine is better leaving group than fluorine. So this is how the rate is. Fluorine is less leaving group than chlorine minus. Chlorine minus is less leaving group than bromine. Bromine is less leaving group than iodine. This is a series. So iodine is a good leaving group. So rate would be increased. I minus is a good leaving group for SN2 reaction. Okay, what would happen if the solvent is changed from acetone to ethanol? What would happen if we change the solvent from this is the rate equation, this is for D, this is E number 1, E number 2 is asking you what would happen if the solvent is changed from acetone to ethanol. Obviously, acetone is polar aprotic solvent, but ethanol is polar protic solvent. So the rate for SN2, this is SN2 reaction, so if you change it to ethanol, the rate would be decreased. It doesn't like polar protic solvent, so the rate would be decreased because you are using polar protic solvent. It is only good for SN1, so in this case it would be decreased because our reaction is SN2. Number 3, alkyl halide is converted to this. This is the same bromopentane, 1, 2, 3, 4, 5, but now instead of a primary, it's changed to a secondary. A secondary alkyl halide is much slower in rate for SN2 than a primary. So rate for secondary, rate is decreased. Rate will decrease because secondary alkyl halide are not good. Tertiary even worse. So secondary alkyl halide, this is secondary, so rate is decreased. What would happen if the cyanide, the nucleophile, is increased 5 times? 5x. The concentration is 5 times high. That means if you come here and look at this, if the rate was just this, when it was 1 times, and if you increase this 5 times, it is multiplication, so the rate would be 5 times. Rate increases 5 times, 5x if you increase the cyano group, the rate would be affected, because in the rate law you have the concentration of the cyano. It is as SN2. Number 5, how about if you increase the cyano by 5 times and the alkyl halide by 5 times? So it means 5 times here, 5 times there. Both are important in the rate law because it's an SN2 reaction. The rate becomes 25 times increased. So we solve the whole problem. This is just summarize the whole SN2 reaction very well. It's a very good example, a very good problem for you to summarize, revise, and look about what is involved in SN2 reaction. So I really like this question. This is the type of question you'll be encountering in this course. So just study this and you'll be mastering the subject in SN2. Okay, let's solve some more problems on SN2 reaction. So in this question, you are supposed to rank the order of increasing SN2 reactivity, the rate of the reaction with different alkyl halides. So we have group 1, group 2, group 3. There are 3 alkyl halides in each one of the groups. So for SN2 reactivity, the alkyl halide is important. The nature of the alkyl halide is important. So first, let's characterize the nature of the alkyl halide. This alkyl halide is a secondary alkyl halide. This alkyl halide is a primary. This alkyl halide is a tertiary. So if you remember our discussion from alkyl halides, in the transition state, both the nucleophile and also the electrophile are implicated in the highest transition state. That's why it's called substitution reaction of a bimolecular type. So steric is very important. So the less steric, bulky, the faster the reaction would be. So in this case, for SN2 reaction, the fastest reaction is this one, and the second one is this one, the secondary one, and the tertiary would be the last. So the tertiary one almost doesn't react in the SN2 type reaction. So the highest rate is this. So primary is much greater than the secondary, much greater than the tertiary. The tertiary one almost doesn't react. So if I just give them a like a ranking or a number, 1, I think that should be just fine. Primary is much greater than secondary and much greater than tertiary. So this is the fastest primary alkyl halide in the SN2 type reaction mechanism. Second, B, you can see here there are alkyl halides. You don't have to know exactly the rest of the molecule. You just focus on where the halogen is, the halide. So this is a tertiary alkyl halide. So that means it reacts the slowest, or almost it doesn't react in SN2 mechanism. This one is still a primary, and this is a secondary. So the order would be primary is greater than the secondary, which is this one, and greater than the tertiary. So this almost doesn't react, but this is the fastest to react as a primary alkyl halide. Here we have a very different type of alkyl halide. This we don't even classify it as primary, secondary, tertiary. This, if you remember in the beginning of the lecture, this is called a vinyl halide, or in this case it's a vinyl bromide. Vinyl because it's directly attached to where the double bond carbon is. So this is sp2 carbon. Remember, all of those primary, secondary, tertiary were on at least sp3. All of them, the carbons are sp3 hybridized carbon. So this is sp3 sigma sp3. But here it's very different from the others. So it is on sp2. It's called vinyl bromide. It's directly attached on the double bond. So it's vinyl bromide. It doesn't almost react in SN2. No SN2 type reaction for this. So it will be the least one. Here you have a primary, because the double bond is far from there. So the halide is also carried on that carbon, which is sp3 hybridized carbon. So it's still a primary. For the SN2, it's a primary. Here, this one is also far from the alkene. That is a secondary type. So the reactivity of this obviously would be primary is the first one, secondary much less reactive. It doesn't almost react, so it doesn't react with the vinyl bromide. It's not tertiary. Sorry, it's not tertiary. Vinyl halides don't react in SN2 fashion. So the nature of the alkyl halide is also important. In previous sections, we have already seen nucleophiles, strong nucleophile, living group, good living group, and poor living group, and so on. In this set of questions, you were able to see the nature of the alkyl halide, how it affects the rate of reaction for SN2. So just briefly, the opposite happens if it was for SN1. For SN1, the fastest would be this. The fastest would be this. So it is the reverse order for SN1. If the question was asking you for SN1, you take exactly the reverse, because for SN1, the carbocation is what determines the stability of carbocation. So tertiary carbocation is easily formed, so the reaction is the fastest for SN1. So at this point, even though the question is for SN2, and these answers are for SN2 electrophiles, but SN1 would be also, could be asked with this. So the reverse order is for SN1. Okay, so we'll continue. Okay, continuing to solve more problems. In this series, pair of reactions are given, and it's asking you between those pair of reactions, which SN2 reaction is faster. So in A, for example, you have ethyl bromide and ethyl chloride, the same nucleophile is given, SN2 reaction. First, let's just give the product. Okay, let's just give the product. This is an alcohol is made, the chloride is substituted, giving the same product. So which reaction is faster? That's what the question is asking. Which reaction would be faster? So here the only difference you can see is the leaving group. So is chloride versus bromide. So plus Br minus plus Cl minus. So the leaving groups are different. So which leaving group is easy to leave, or a good, better leaving group? So between these two, HCl is a weaker acid than HBr. HBr is a stronger acid, so the base, as a base, Br is weaker. chloride is much stronger. So chloride would be a poor leaving group. So the reaction which is faster would be Br with Br. So ethyl bromide with hydroxide nucleophile, the nucleophile is the same, but the leaving group are different. So bromo leaves much easier than the Cl. So that's the answer. Bromide leaves easy. You have here one, two, three propyl bromides. They are the same electrophiles or alkyl halides, but you are given two different nucleophiles. One is a strong base OH minus and water molecule. Water is a neutral molecule. As a nucleophile, it is not as strong as OH minus. Let's just give first the product. Anyways, this is what happens. Here we have OH2 plus. So in this reaction, which one is faster? Obviously, the stronger nucleophile would be faster. At the end of the day, once the proton is gone, they would be the same product, but this is faster. Because here the nucleophile strength is important. Here the leaving group was what our focus was. Here the nucleophiles are being compared. So hydroxide, which is OH minus, is stronger as a base and stronger as a nucleophile as well. Here we have also again the same electrophile or alkyl halide. The product, let me give the product of that. So whenever you are given sodium hydroxide, I have repeatedly said that the cation is just a spectator ion. It doesn't do in the nucleophilic substitution. So this is OH minus and sodium plus. So basically this is sodium plus OH minus. So you should just focus on the OH minus. That is a nucleophile. So the product is OH. Here you have also the same thing. You have sodium acetate, and the sodium is not part of the nucleophile, so the product is CH3. So here now, between the acetate anion and OH minus. OH minus, what we are comparing is the nucleophile. This versus that acetate anion. Remember now, OH minus, which is the hydroxide, is a very strong base than the acetate. The acetate is a weaker base, even though it has the same O minus charge over there, because if you just push these electrons into this into that, this actual structure is resonance stabilized. So that resonance stabilization makes this charge not available to do the substitution reaction. Hence, this is the faster reaction, because OH is a very strong base than the acetate anion. The acetate anion is less basic because the electrons are not available, because they are resonance stabilized. Here we have iodo leaving group, or the alkyl halide is the iodide, both of them. Here you have the same nucleophile. Remember, you have the same nucleophiles. Here you have two different solvents. Now, the solvent becomes important in this case. First, let me just give the product. The expected product is the same product, because it's the same nucleophile. But which one is faster? This is a reaction, remember. For SN2 reaction, you can run your SN2 reaction in polar aprotic solvent. But methanol is polar protic solvent. So this is not faster. DMSO is polar aprotic. Doesn't have a hydrogen on it that can hydrogen bond. So this is faster. But this one, methanol, is polar protic solvent. So polar protic solvents are not good for SN2 type reactions. Okay. Now, one last question here is you have two nucleophiles, that is etoxide, strong base, etoxide, like alkoxide. These are RO minuses. They are very strong. Here it is RO minus as well. But here the difference is in terms of the nature of the alkyl halide. Here you have a secondary alkyl halide. Here you have a primary alkyl halide. So substitution reaction SN2 type is very happy to be done with primary alkyl halide. Let me just give the product. Product looks like OCH2 CH3, but here the product is OCH2 CH3. So the reaction which would go faster would be the primary alkyl halide. Reaction with a primary alkyl halide is much faster. So this problem also gives you a lot of different concepts. The nature of the alkyl halide, nature of solvent, the nature of the nucleophile, nature of leaving group. So it summarizes everything that you need to know in a substitution reaction. So please review until you understand all of the reasons why one reaction is faster over the other. We'll continue with more. Okay, now continuing with problem solving. Now we go to deep into the stereochemistry of an SN2 reaction. That means SN2 reaction, if you remember, it is a backside attack, and the products are formed. If you start with an enantiomerically pure compound, there is inversion of configuration. But for SN1, there is a stereochemical outcome where the carbocation can be attacked from any phase. That means it will give you a 50-50 chance of racemization. So now we are just dealing with SN2 where there is inversion of configuration. What it means is whatever initial alkyl halide after nucleophilic substitution, if it was an R, the product should be an S. If it starts with an S, it will give you an R. So that's why I said here attention to the stereochemistry. So in nucleophilic substitution, if you are given a chiral or an enantiomerically pure compound, you should be very careful to give the substitution product because it is a backside attack. Here, for example, you have a compound, alkyl halide, chloro is the leaving group. So this compound is an S compound because this carbon is substituted to 1, 2, 3, 4 different species, so 4 different groups. So this is an S. So I want you, we have already passed that chapter where stereochemistry to assign R and S. But in any case, you will be substituting that chloride using this methoxide. So this is your nucleophile, this is the electrophile. So the product for this, I'll just give you the product so that you just look at that and see how the product is changed. So what happens is the methoxide comes and attacks from backside, from this side, okay? That means all of whatever it's coming from, all of those would face the other way. So the product looks like when all CH3 comes from backside, from this side, this leaves. That's the mechanism of it. So what the structure of the product looks like is that the OCH3 comes from backside, hydrogen goes back, and the D would remain here. So D remains here, right? But the methoxide, the nucleophile comes from back, pushes the hydrogen to the inside of the plane of the board, so the methoxide remains on the plane of the board. So the easiest way to do is, whenever you have a nucleophile, just bring it opposite to where your leaving group is. Then you would make a bond, and that hydrogen obviously would be at the back. So now this obviously should be an R stereochemistry. So let's see, the substitution product is R. This is because of inversion of configuration. This is only for stereochemically pure compound. If you have an enantiomer, the enantiomer would be converted. That carbon would be only affected where the leaving group is on. So this is priority 1. If you remember, this is priority 2. This is D is deuterium, a heavier hydrogen, and 4 is the back. So if we just go that way, this is on R. So we are right. So this compound, after substitution of the halide, has undergone inversion of configuration. So always remember, with SN2 reaction, inversion of configuration. Always remember that. Okay, the next question is just to give a product of this. There is no any chiral center for this compound. It's 1, 2, 3, 4, F5 carbon alkyl halide. It is actually iodopentane. So the hydroxide will just kick out that and gives you this product. 1, 2, 3, 4, 5. So nothing, no stereochemistry. So there is no need to pay attention for any stereochemical changes. Here also you have a stereochemistry on this carbon, but not on the carbon that contains the halide. So there is no need, you don't change anything because the substitution happens on this carbon, not on that carbon. So the stereochemistry still remains the same. The stereochemistry changes if the leaving group is on that carbon, on the chiral carbon. So here we have 1, 2, 3, 4, 5, 2, 3, 4, 5. So this is the product, but here you should write exactly how it was. That's the methyl group, and this is the hydrogen group. Okay, this is carbon, CH3. Okay, now we have another one. Here actually the nucleophile is given as a cyano, and the question asks you the nucleophilic substitution on this carbon. Right now the halide is on a stereochemically pure chiral center. So now attention, there is a stereochemical change in this case. So what happens is the nucleophile comes from here, so it would be replacing Br. That's why. So now first let's see what the stereochemistry of this thing is. Bromine is 1, priority 1. So if I go this way, this is 2 because it has carbon here. This one is the third one, priority 4th. So going from 1 to 2 like this is an R. So our product should be an S product. So now the cyano comes and attacks this carbon, this leaves. So the substitution product looks like, oh, these are not good, sorry. So it is this. If I just did cyano here, and obviously this is hydrogen now, and you don't change anything on that carbon, CH3. Let's see what we have. This is priority 1. Priority 2 is this. Priority 3 is this. Priority 4 is this. So if you just switch CN with this and hydrogen at the back, so it would become R like that, but this is an S. So that is a product, a substitution product with proper stereochemistry. So remember the assignment, and that's something we have done long time ago, and you need to remember how to do that. So that is an S, you started with R. After substitution there is inversion of configuration. Inversion for SN2 reaction. So as a summary for all SN2 reactions, if you have a chiral center, that chiral center, if it happens to be where the halide or the leaving group is on, there would be a change in stereochemistry. That is called inversion of configuration. But for SN1, we haven't done anything SN1. For SN1, there is racemization, meaning that you generate both R and S. So the stereochemistry gets racemized, meaning a mixture of 50-50 of both stereoisomers. So this is a very good set of questions to show you about inversion of configuration. So with the next video, we'll continue also more on carbocations, more SN1 reactions, solvents, and so on. So that would give you a solid foundation in nucleophilic substitution reactions. Thank you.